Welcome back to the Deep Dive. Today we're tackling something pretty fundamental to, well, almost every industrial process out there: flow measurement. We're digging into the kind of dense technical specs that, let's be honest, can be intimidating.
That's right. We're talking about the nitty-gritty of how industries measure the flow of gases, liquids, steam, things that are often hot, under pressure, sometimes hazardous. It's not just about getting a number, it's about getting the right number reliably.
Exactly. And today our mission is to unpack three specific advanced types of flow meters: thermal mass, vortex whirl, and electromagnetic. We'll get into how they work, where you'd use them, what you really need to know about installing them, and the safety side, which is critical.
And it's important to understand why there are different types. Industrial processes aren't always neat and tidy. What works for clean, dry air might completely fail with corrosive sludge or high-pressure steam. You need the right tool for the job.
So our goal for you, listening in, is to get beyond just the names. We want you to understand the how these devices actually measure mass flow or volume flow or even energy flow, often under some really tough conditions.
High temperatures, changing gas mixes, explosive atmospheres. Yeah, the challenges are real.
Okay, so let's lay out the three main technologies we're focusing on today. First up, thermal mass flow meters. These are kind of the specialists for gases, right? Giving you that direct mass flow reading.
Correct. Pillar number one, thermal mass for direct gas mass flow. Then second, we have the vortex and swirl meters. I think of these as maybe the versatile workhorses. They handle liquids, gases, steam, but often need a bit more help, some compensation to get to mass or energy flow.
Right, that makes sense. Compensation is key there. And our third pillar.
That's the electromagnetic flow meters, the MagMaster series we'll discuss. These are really specialized for conductive fluids. Think water, wastewater, slurries, built tough, designed for infrastructure.
Okay, three distinct approaches. Let's dive into the first one. Thermal mass. We're looking at the SensiFlow FMT series here, designed mainly for gases. You mentioned the core principle is the hot film anemometer.
Yes, that's the heart of it. It's a thermal principle, and the elegance lies in how it gets you directly to mass flow. Not volume, but the actual amount of substance moving through. That's often what matters in, say, chemical reactions or custody transfer.
So how does it work? How does heating something up tell you how much gas is flowing?
Well, imagine two tiny sensors, platinum resistors, in the gas stream. One is heated, let's call it RH, and the system works constantly to keep it at a specific temperature difference above the other sensor, RMG, which just measures the gas's temperature.
Okay, so one sensor is always kept, say, 50 degrees hotter than the gas itself.
Exactly. Now, as the gas flows past, it cools down that heated sensor, RH. It carries heat away. The electronics then have to supply more electrical power, more heating current, IH, to maintain that constant temperature difference.
Ah, like blowing on hot soup cools it faster.
Precisely that principle. The faster the gas molecules move past, the more heat they strip away. The meter isn't measuring temperature directly for flow. It's measuring the electrical power needed to counteract that cooling effect.
And that power relates directly to the mass flow.
Directly. Because the amount of heat carried away depends on the number of gas particles hitting the sensor surface. More particles per second means more mass flow, which means more cooling, which means more heating power is needed. So that heating current becomes your direct linear signal for mass flow rate.
Okay, now here's what seems like the big payoff, especially for anyone who's dealt with gas calculations before. No extra compensation needed.
That's the aha moment, exactly. Because it's fundamentally measuring mass, you can get to standard volume flow rate, the volume the gas would occupy at standard temperature and pressure, without needing separate pressure and temperature sensors feeding into the calculation.
Which you absolutely need with traditional volume meters, right?
Yeah.
Because gas density changes so much with P&T.
Correct. With thermal mass, if you know the gas's standard density, the meter can display standard volume flow directly. It cuts out hardware, complexity, and potential error sources. It's a huge simplification.
And the specs seem to back that up. Accuracy typically better than, what, 1% of reading for common gases?
Yeah, often around plus or minus 0.9% for things like air or nitrogen. But the dynamic range, the turn down, is also really impressive.
Up to 1.150 or 1.100. What does that mean in practice? Why is such a wide range useful?
Think about something like controlling gas flow to a burner or measuring flare gas. You might have huge peak flows during startup or upsets, but then very low trickle flows during standby or normal operation. That 1.150 range means the same meter can accurately measure both the massive peak and the tiny minimum flow. That's critical for control, safety, and environmental reporting.
Got it. And the FMT 400 series comes in a couple of flavors.
Right. There's the FMT 400 VTS. That's your standard model for general process stuff, compressed air systems, chemical processes, air separation plants, even handling hydrogen flow.
And the FMT 400 VTCS. The CS suggests something different.
Hygienic. That's for food and beverage. Same principle, but built with materials and connections suitable for sanitary applications. Think smooth surfaces, specific fittings like DIN 11-Profen51. For gases like the clean air, nitrogen, CO2, or oxygen used in food processing and packaging.
Okay, makes sense. Now, even though there are no moving parts, installation still matters, doesn't it? We still see notes about needing straight pipe runs.
Absolutely. The flow profile heading the sensor still needs to be uniform for the heat transfer to be consistent and the reading accurate. The standard recommendation is usually based on ISO 5167-1, needing about 15 times the pipe diameter, DN, of straight pipe before the meter, and 5 DN after.
15 DN upstream, 5 DN downstream. That sounds manageable.
It often is, but, and this is a big but, if you have a major flow disturbance right before the meter, like a partially closed valve, a control valve, or a sharp bend, that upstream requirement can jump dramatically. The docs mention up to 50 times DN.
50 DN. Okay, that's a huge difference. That straight pipe requirement seems like a recurring theme in flow measurement.
It really is. Achieving a stable, predictable flow profile is often the biggest practical challenge. And that leads us nicely into our second category, the vortex and swirl meters, the FSX 400 series.
Right. If thermal mass is the gas specialist, these are the generalists, handling liquids, gas, steam.
Exactly. Much more versatile in terms of what they can measure. But, and here's the trade-off, you generally lose that direct mass measurement capability. You're back to needing compensation for things like mass or energy flow.
Let's talk about the compensation. The FSX 400 meters, they directly measure volume flow under the actual operating conditions, right? Pressure and temperature in the pipe.
Yes, the primary measurement is operating volume flow, but very often what you need for process control, billing, or reporting is standard volume flow, or mass flow, or even energy flow, especially with steam.
So how do you get from operating volume to those other values?
Through calculation. The meter's internal computer does the math, but it needs extra information. You either need built-in sensors for pressure and temperature, or you need to feed those values in from external transmitters.
Okay, so if I'm using an FSX 400 for, say, natural gas, and I need standard volume flow, I have to provide the operating pressure and temperature.
Correct. You configure the meter for gas CD norm vol mode, and you supply those P&T inputs. The meter then uses gas laws, potentially with compressibility factors, to calculate the standard volume.
But wait, if I need standard volume flow for gas, why wouldn't I just use the thermal mass meter we just talked about, which does it directly?
Good question. The answer usually comes down to robustness or pipe size. Thermal mass meters, especially the hot film type, can be sensitive to dirt, moisture, or corrosive elements in the gas. Vortex meters are generally tougher. Also, thermal mass meters are often limited to smaller pipe sizes, while vortex meters go much larger. So you accept the compensation complexity in exchange for handling tougher conditions or bigger pipes.
Okay, that makes sense. What about steam? That seems like the trickiest one, given how density changes dramatically near saturation.
It is complex. For steam, particularly if you need accurate mass or energy flow, the FSX 400 relies on a built-in standard called IAPWS IF97. That's the internationally agreed-upon set of equations and data for the thermodynamic properties of water and steam.
So you tell the meter the pressure and temperature, and it uses this IAPWS standard to look up the exact density and enthalpy needed for the mass and energy calculations.
Precisely. And you have to tell it whether you're dealing with saturated steam or superheated, overheated steam because the calculations are different. It uses the pressure and temperature inputs against the IAPWS IF97 tables or equations for that specific steam state.
What happens if you get that wrong? So you configure it for saturated steam, but the process is actually running superheated.
The meter will likely throw an error, maybe something like wrong steam type. The density calculation will be incorrect, sometimes significantly, and so your mass flow and energy flow readings will be wrong. Getting the configuration right, matching it to the actual process conditions is absolutely vital.
It sounds like the details really matter with these compensated meters, which brings us back to installation and that straight pipe issue. This seems to be a major dividing line between the two types within the FSX 400 series. Vortex Master versus Swirl Master?
It's probably the single biggest factor in choosing between them, often more than cost. The Vortex Master, the FSV models, relies on a very clean, predictable pattern of vortices shedding off a bluff body, a shutter bar, placed in the flow. Think of a flag fluttering in the wind. It needs smooth airflow.
So if the flow coming into the Vortex Master is turbulent or swirling, the vortex pattern gets messed up.
Exactly. It becomes unstable, chaotic. The meter can't reliably count the vortices, so the reading becomes inaccurate or fails altogether. This is why it demands those long, straight pipe runs to condition the flow to smooth everything out before it hits the shutter bar.
And how long are we talking? You mentioned 15 DN upstream, 5 DN downstream as a minimum.
That's the baseline, yes. After something simple like a single standard elbow, but the killer is if you install it after a valve, especially a control valve or a pump or two elbows close together in different planes.
The really disruptive stuff.
Right. In those cases, the required upstream straight length jumps to a minimum of 50 times DN. 50.
50 times the diameter. Let's picture that. A 6-inch pipe, DN 150, that's 50 times 150 millimeters, 7.5 meters. Over 24 feet of perfectly straight, unobstructed pipe needed before the meter.
Exactly. In a new plant, maybe you can design that in. But in an existing facility, trying to retrofit, finding 7.5 meters of straight pipe run is often completely impossible without massive, expensive repiping.
That's where the Swirl Master comes in then, the FSS models.
Precisely. The Swirl Master is engineered differently. It actually induces a controlled swirl in the flow internally, and then measures the frequency of that swirl. Because it creates its own stable flow pattern, it's much less sensitive to upstream disturbances.
So it essentially conditions the flow itself.
In a way, yes. It doesn't need the long, straight run to receive a perfect profile. It creates a measurable pattern regardless.
And what does that do to the installation requirements?
It slashes them. The standard requirement for a Swirl Master drops to just 3 DN upstream and 1 DN downstream.
3 DN versus potentially 50 DN. That's incredible.
It's the difference between we can fit this meter here and we need a major project. And the specs even suggest that if the upstream elbow has a large radius bigger than 1.8 times DN, you might not need any straight inlet or outlet sections at all.
So the Swirl Master is clearly the go-to choice when space is tight or the existing piping is messy.
Absolutely. It's designed specifically for those constrained installation scenarios.
One more quick point on the FSX 400 before we move on, cavitation and liquids.
Yes, crucial for liquid applications. If the pressure in the pipe drops too low after the meter, perhaps due to a downstream valve or elevation change, the liquid can actually start to boil or vaporize, forming bubbles. That's cavitation.
And that's bad because
2 reasons. First, the bubbles mess up the flow measurement completely. You're measuring a mix of liquid and gas. Second, the collapse of those bubbles can be incredibly damaging, physically eroding the meter internals and the pipe itself. So you have to ensure there's enough back pressure downstream to keep the liquid well above its vapor pressure at all times.
Okay, installation and maintaining liquid phase, critical points. Now let's circle back to thermal mass, but look at the more advanced digital versions, the SensiMaster FMT 430 and 450. What sets these apart from the basic FMT 400?
The big leap is in the electronics and processing. They use fully digital signal processing. What that means for the user is better performance, especially when things are changing. Faster response times, better stability, and improved accuracy even if the gas temperature or pressure fluctuates, or if the gas composition shifts slightly.
So more resilient to real-world process dynamics, and they seem to offer more data output.
Yes, that's a key feature. They provide not just the primary mass flow signal, but also secondary values like the actual heating power being used, the temperature of the gas medium from that RMG sensor, and even the temperature of the heater element itself. And these can often be output simultaneously over digital protocols like HART, Modbus, or Profibus.
Having that gas temperature reading directly from the flow meter seems handy. Saves installing a separate temperature sensor.
Often, yes. Since it's already measuring gas temperature accurately as part of its core function, you get that value essentially for free. It simplifies the overall system design, reduces wiring, and potentially saves cost.
Now, the FMT 450 has this application selector. You described it as a kind of internal gas cocktail mixer.
Yeah, that's a decent way to think about it. The FMT 450 has a built-in database of gas properties. It allows the user to pre-configure up to 8 different applications or gas mixtures. Each mixture can contain up to 10 different component gases.
So if a plant processes different gas feeds on different days, say a methane-rich stream today, and ethylene mix tomorrow, they can just select the pre-configured application.
Exactly. Instead of having to manually reparameterize the meter or use complex external calculations, they just switch the active application profile via the interface or digital comms. The meter then automatically uses the correct properties for that specific gas mix in its calculations. The FMT 430 offers a simpler version supporting 2 applications.
That sounds particularly useful for things like natural gas, where the composition can vary quite a bit.
It is. It helps maintain accuracy when the gas properties aren't perfectly constant. However, there's an important footnote here regarding certain gases,
Which ones?
specifically hydrogen, H2, and helium, E, if your process gas contains more than about 10% of either H2 or He by volume, the standard calibrations might not be accurate enough. These gases have very different thermal properties compared to air or nitrogen.
So for high hydrogen or helium applications?
Optional process gas calibration is highly recommended. This means the meter is calibrated at the factory using the specific gas mixture it will encounter in the field, ensuring the highest possible accuracy.
Okay. The FMT 450 also boasts some advanced diagnostics. Let's talk about VeriMass sensor check.
VeriMass is basically an onboard health check for the sensing elements. When the meter is installed or during a maintenance check, it records a fingerprint based on the thermal characteristics, temperature response, heat conductivity of its own sensors under known conditions, like zero flow.
And then later.
Later, you can trigger another VeriMass check. The meter compares the current fingerprint to the stored reference. If there's a significant difference, it could indicate sensor drift, contamination building up on the sensors, or even physical damage. It provides an alert, prompting closer inspection or maintenance. It's a valuable tool for predictive maintenance and ensuring ongoing accuracy, but importantly, it has to be done at zero flow.
Makes sense. And the FillMass batch function. Sounds like it's for filling applications.
Yes, specifically for short-duration batch filling, like filling tanks or cylinders, usually processes longer than about 3 seconds. When you shut off a valve quickly at the end of a fill, there's always a small amount of overrun fluid that passes the meter after the shutoff signal, but before flow completely stops due to inertia.
So the batch total might be slightly off.
Right. FillMass is designed to measure that small overrun quantity after the valve closure signal, usually via a digital input, and automatically corrects the final batch total. It gives you a more accurate measure for critical dosing or custody transfer applications.
Very clever. Okay, let's completely shift gears now. From the precise world of gas measurement to the often rough and tumble environment of water and wastewater. We need to talk about the MagMaster series, the electromagnetic flow meters.
A totally different principle, yes. We're now using Faraday's law of induction. You create a magnetic field across the pipe, and as the conductive fluid flows through it, it acts like a wire moving through the field, inducing a voltage.
And that voltage is proportional to the flow velocity.
Exactly. The faster the fluid moves, the higher the voltage generated between 2 electrodes mounted in the pipe wall. The key requirement here, though, is conductivity.
The fluid has to be able to conduct electricity. How conductive?
The minimum threshold is typically 5 microsiemens per centimeter.
Give us some context. What fluids meet that and what fluids don't?
Well, 5 Siemens is pretty low. Most tap water, river water, wastewater, sewage, and many industrial slurries and chemical solutions are well above that, so they're easily measurable.
What was that then?
The big ones are hydrocarbons, oils, fuels, solvents. They're generally non-conductive. Also, highly purified or demineralized water can sometimes drop below that threshold. But for the vast majority of water-based applications, conductivity isn't an issue.
Okay. Now, the big selling point for MagMaster seems to be its incredible robustness and suitability for infrastructure. The IP68 rating, for instance.
Right. IP68 or NEMA 6P means the sensor is fully submersible. It can literally operate underwater indefinitely. In the world of buried pipelines and utility vaults that often flood, this is huge. It just keeps working.
But even more significant might be the variable design.
Yes. This changes the installation game completely. Traditionally, putting a flow meter on a large buried water main meant building an underground concrete vault or chamber. This was expensive, time-consuming, and created a confined space for future maintenance.
The MagMaster avoids that.
Entirely. The sensor itself is designed to be directly buried in the ground, just like the pipe. You excavate, install the meter section, and backfill. No vault needed. This drastically cuts installation costs, speeds up projects, and eliminates the long-term maintenance and safety issues associated with chambers.
That's a massive practical advantage for utilities. What about grounding? Electromagnetic meters usually need good grounding, right?
They do for a stable reference potential. Traditionally, this meant installing grounding rings or flanges, which adds complexity and potential leak paths. The Magmaster often incorporates built-in grounding electrodes that make direct contact with the fluid.
So it grounds itself through the water.
Effectively, yes. It eliminates the need for those external grounding accessories, simplifying installation further and removing another potential point of failure or error.
Let's talk performance,
Yeah.
especially for municipal water. That turndown ratio is listed as 1500.1. That seems enormous.
It is, and it's incredibly important for water networks. You need to measure the high flow rates during peak demand times, accurately, obviously, but you also need to accurately measure the very, very low flow rates that happen typically at night.
Why are those low night flows so important?
Leak detection. The minimum night flow is a key indicator of water loss in the distribution system. If your meter can't accurately register those tiny flows that over 8,000th of the maximum flow, you can't effectively track down leaks, which costs utilities a fortune in lost water and treatment costs. And these meters cover a huge size range, too, from half an inch up to nearly 7 feet in diameter.
Wow. Okay, one last piece on Magmaster.
Yeah.
Maintenance and calibration. If the sensor is buried, how do you check if it's still accurate over time, as regulations often require? Digging it up seems impractical.
That's where the CalMaster compatibility comes in. CalMaster is an in-situ verification tool. It allows a technician to connect a device to the Magmaster's transmitter, which is usually accessible, not buried, and run a series of electronic tests.
What do these tests check?
They verify the integrity of the sensor coils, the electrode circuit, and the transmitter's signal processing against the original factory calibration data. It essentially confirms that the meter hasn't drifted and is still performing within its specified accuracy.
Without interrupting flow or excavating.
Correct. No shutdown, no digging. It provides a traceable verification certificate, satisfying regulatory requirements and saving enormous amounts of time and money compared to traditional wet calibration. It's a complete solution for ongoing accuracy assurance.
Okay, that covers the three core technologies. Yeah. But now we need to zoom in on some critical details that apply across the board: installation, safety, configuration. These often get overlooked, but are vital for reliable operation.
Absolutely. These are the practicalities that make or break a successful installation, regardless of the measurement principle. Let's start with environmental conditions.
Temperature seems key. Standard ambient range is often negated at 20 to plus 70 degrees C.
Typically, yes, though options for lower temperatures, down to -40°C, are often available. But a really important point is avoiding direct, strong sunlight on the transmitter housing. The electronics inside can get much hotter than the surrounding air, potentially causing drift or even failure. Sun shields are often recommended or required in hot, sunny locations.
And it's not just ambient temp. The connection cable needs careful thought too, right?
Critically important. The cable's temperature rating must be sufficient for both the maximum ambient temperature and any heat conducted from the process fluid through the pipework or sensor housing.
So if you have hot steam inside the pipe, even if the air is cool, the cable connection point might get quite hot.
Exactly. The specs usually provide guidance, like if ambient is 70 C and medium is hotter, use cable rated for 90 Cs or similar. Using underrated cable is a recipe for insulation breakdown and signal failure down the line.
Okay, that's thermal stress. What about mechanical stress?
Two main things: installation stress and vibration. The meter must be installed without any twisting or bending forces from misaligned pipes or flanges. The pipework needs to line up properly. Forcing it can distort the meter body and affect accuracy, or worse, cause leaks.
And vibration. You mentioned this particularly for vortex meters.
Yes, external vibration from pumps, motors, or even just turbulent flow in poorly supported pipes can be a killer for vortex and swirl meters. The vibration can interfere with the detection of the flow-induced signal, the vortices or swirl. It's essential to install pipe supports close to the meter on both sides to isolate it from these vibrations.
Right, good support is crucial. Now let's talk safety, specifically hazardous areas. These meters are often used where flammable gases or dusts are present.
Non-negotiable territory. The devices we're discussing, the FMT and FSX series particularly, come with a whole raft of hazardous area certifications: ATEX for Europe, IESEX internationally, FM and CSA for North America, sometimes others like NEPSI for China.
And these cover different protection methods, like intrinsically safe, Flameproof.
Exactly. You'll see markings like XGIA or XI for intrinsic safety, which limits the electrical energy to levels below what could ignite a specific gas or dust. Then there's XEB or XD for flameproof enclosures, designed to contain an internal explosion and prevent it from igniting the surrounding atmosphere. And others like XNA, non-sparking, or NI, non-incendive, for lower risk Zone 2 areas.
The choice depends on the zone classification, how likely an explosive atmosphere is to be present. But the temperature class, the T rating, seems like a major operational constraint.
It is. The T class, T1 down to T6, defines the maximum surface temperature the device is allowed to reach under fault conditions. T6 is the strictest, meaning the surface can't exceed 85 degrees C because some gases ignite at very low temperatures.
And this T-class limit directly impacts the allowable operating conditions.
Absolutely. It links the certification to the actual process. For example, a meter certified as T6, intrinsically safe, XIA, might have its maximum ambient operating temperature restricted to, say, 44 degrees C, even if the standard range is 70 degrees.
Why would the ambient limit be so low for T6?
Because the total surface temperature is a combination of internal heating, even the low energy in IS circuits, plus the heat absorbed from the surrounding air, plus heat from the process medium. To guarantee the surface never exceeds 85 degrees C, even under fault conditions, you have to limit the contribution from the ambient air if you want that T6 rating. This often forces design choices like using specific safety barriers or mounting the transmitter remotely.
Okay, T-class interaction is critical. What about practical safety warnings during maintenance?
Two really jump out from the manuals. First, never open the housing in a hazardous area while the power is on. You must isolate the power externally and wait. Often, a minimum of 2 minutes is specified for any stored energy and capacitors to dissipate before opening the enclosure.
Standard practice, but easily forgotten. What's the second one?
Electrostatic discharge, or ESD. Particularly relevant for enclosures made of painted aluminum.
Why painted aluminum?
Because the paint is an insulator, and rubbing it, like cleaning with a dry cloth, can build up a static charge on the surface. Aluminum itself is conductive. In very dry conditions, typically below 30% relative humidity, this stored static charge can become large enough to cause an incendiary spark when it discharges, potentially igniting a flammable atmosphere.
So how do you clean them safely?
The manuals are explicit. Only clean with a damp or moist cloth. The moisture dissipates any static charge as it's generated, preventing the buildup. It seems minor, but it's a serious ignition risk if ignored.
Good points. Let's quickly cover electrical connections and communication. They seem pretty flexible.
Yes, designed for global use. You typically see options for both metric cable glands, like M20, common in IEC standards, and NPT threaded connections, like 12-inch NPT, used widely in North America.
And communication protocols.
A wide range. Standard 420 NUA analog output, often with HART overlay for digital configuration and diagnostics. Then you have the major digital field buses. Modbus RTU over RS-485, Profibus DP, and Foundation Field Bus. Usually these are implemented via interchangeable communication modules in the transmitter.
So pretty adaptable to whatever control system is in place. But there was a specific security warning about Modbus and Fieldbus.
Yes, and this is crucial in today's world of industrial cybersecurity. The documentation clearly states that Modbus and standard Fieldbus protocols are inherently unsecured. They lack built-in encryption or authentication, meaning the end user bears the responsibility for securing the network these devices connect to. You can't just plug them into an open network without considering the risks. Appropriate network segmentation, firewalls, and other security measures are essential if these protocols are used.
A critical point for system integrators and planned network architects. Lastly, configuration on site. There's mention of easy setup and capacitive buttons.
Right. The aim is to simplify commissioning. Easy setup guides the technician through the most common parameters needed to get the meter running. And the capacitive buttons are neat if the meter has the right display option, like the L2 indicator mentioned. These buttons work through the glass cover of the housing.
Ah, so you don't need to open the enclosure to make basic configuration changes.
Exactly. In a hazardous, wet, or dirty environment, that's a huge plus. You maintain the integrity of the enclosure and its safety rating while still being able to tweak settings.
Okay, we've covered a ton of ground. Let's try to synthesize this. We've looked at 3 very different flow measurement technologies. How does someone choose?
It boils down to matching the technology to the need, considering all the constraints. If your primary need is direct, accurate mass flow of clean gases, and you want to avoid external P&T compensation, thermal mass, like the FMT series, is likely your best bet. Just be mindful of potential sensitivity to dirt and the need for special calibration for gases like H2 or Hay.
Okay. And if you need more versatility, liquids, gases, steam, or if the conditions are a bit rougher or the pipes are larger.
Then you look at Vortex or SWOR meters, FSX 400. They offer that robustness and media flexibility, but you have to accept the need for compensation using things like IAPWS IF97 for steam to get mass or energy flow. And the huge deciding factor is installation space.
Right. The Vortex Master needs potentially massive straight pipe runs up to 50 DN, while the SWOR Master is the champion of tight spaces, needing only 3 DN or sometimes none. That installation constraint is often paramount.
Absolutely. And finally, if you're dealing specifically with water, wastewater, or conductive slurries, especially in large pipes or buried infrastructure,
Then the MagMaster is the purpose-built tool. Its strengths are extreme robustness, IP68 variable design-saving volt costs, the massive turn-down ratio, 1500.1, vital for leak detection, and the CalMaster in-situ verification capability for easy compliance and maintenance.
so the core takeaways for anyone selecting or installing these are: understand the measurement principle, direct mass versus compensated volume, rigorously assess the installation requirements, especially those straight lengths, and meticulously adhere to the safety constraints dictated by the hazardous area approvals and temperature classifications.
Excellent summary. Now, for our final provocative thought. We spent a lot of time talking about the physical challenges needing long, straight pipes, dealing with high temperatures, ensuring electrical safety in hazardous zones.
All stemming from the fact that these sensors, the thermal elements, the shetter bar, the electrodes have to be inside the pipe in direct contact with the fluid to work.
Right. So thinking ahead, how might future developments in truly non-contact flow measurement change the game? Imagine technologies, maybe using advanced ultrasonics that can map flow across the entire pipe diameter from the outside, or sophisticated laser optics that can sense velocity without ever touching the fluid.
Could such technologies eventually eliminate the need for these complex, demanding installation requirements? Could they bypass the challenges of material compatibility, sensor fouling, and even some of the temperature and pressure constraints we've discussed?
It's definitely something to think about. Could advances in physics and sensing ultimately simplify industrial flow measurement, making setups easier, safer, and perhaps even more accurate by looking at the flow in a completely new way? That's something for you to ponder.